Hello, good morning, and welcome to this talk on the regional variation of corneal stiffness in cases with keratoconus progression. My name is Ahmed Elsheikh. I'm a professor of biomedical engineering at the University of Liverpool. Before I start, I would like to declare that I am a consultant with Oculus, and I also have received research funding from the same company. 3 years ago, you may remember that we presented our work on the stress strain index, or the SSI, which is intended as a measure of corneal material stiffness. The work basically came from observations of our experimental work on corneal tissue, and we found that corneas was different from different age groups, presented similar stress strain behavior, and using a simple stretching factor in the strain direction could move us from one plot to another. And using this very simple observation, we came up with the idea that the SSI would be equal to that stretching factor. So if the corvus tells me this person has a stress strain index, let's say, of 0.1, then I can take the benchmark stress strain plots and divide the strain values by 0.8, and this will give me a new plot. And because you know the full stress strain curve, you can then get the E tangent at any stress or strain level. We've tried the SSI in populations of keratoconus with different disease progression stages. We tried mild, moderate, and severe cases, as well as permafrost cases, and also healthy corneas. And we could find clear deterioration in SSI with disease progression. And this possibility of using SSI as a biomarker for KC progression in individual patients. An important development of this work was the turning of the SSI from a single value into a 2D map. And in doing this work, we relied on two things. The first is an observation that the corneal biomechanics or stiffness relies completely on the microstructure or the collagen fibril content. So if you have two locations with different collagen fibril content, you would expect that the one with the higher content would have higher stiffness relative to the other location. So this is quite important. The other thing is that, which is really good news, is that the microstructure data, there is already microstructure data available for healthy corneas, and it is in the literature, and it is quite consistent. When it comes to keratoconic eyes, there is a bit of a challenge because, of course, the disease creates a cone. The cone has a smaller thickness, the microstructure has been disrupted. So how do we deal with this? Here we have a number of observations which we can rely on. The first thing is that the microstructure outside the cone seems to be unaffected by the disease progression, which is really good news. It means that we don't have to worry about the healthy areas of the keratoconic cornea or the areas outside the cone. The second observation is that there is strong correlation between three parameters: the cone area, the minimum thickness of the cornea, and the central curvature of the cornea with the reduction in fibril density. So if we can do some topography analysis or tomography analysis of the cornea, as well as find the location of the cone and the area of the cone, we can estimate the reduction in fibril density within the cone and therefore the stiffness loss within the cone. So using this information, I can show you example maps of a healthy cornea where there is no fibril reduction, a mild keratoconus with 20% fibril reduction. And then if you look at the bottom left, you will see a case with moderate keratoconus where the fibril reduction is as high as 40%. And then in the bottom right, you get the advanced keratoconic case with fibril reduction of 60%. And you can see clearly that as the keratoconus disease progresses, the stiffness within the cone seems to be affected, while actually the areas outside the cone seems to have seen little change. The new results which I would like to share with you here is whether we can use this to assess keratoconus progression. And here I'm showing you a case with mild progression between two stages. So here SSI was measured, topography was measured before progression, and then SSI was measured and topography was measured after progression. The difference between these two stages represent a case of mild progression with very small deterioration in SSI, 0.05, and very small change in Kmax of 0.3 diopter. The really interesting thing is the differential map, which you see on the bottom right. And here you can see that outside the cone, there has been almost no change. Most of the change is happening within the cone. If you then move to the next case, where there is moderate progression with SSI reduction of 0.13 and Kmax increase of 1.5 diopters, here again you can see that the change outside the cone is very limited. Most of the change is happening inside the cone. And finally, a case with severe progression. Again, the change in SSI is bigger, change in Kmax is bigger, but still the change in the SSI outside the cone is pretty limited. So in all three cases, and actually in all the cases we have covered, we found that the change in stiffness outside the cone was pretty limited, and most of the change, the great majority of the reduction in stiffness, was taking place within the cone. So looking at the whole population, the 29 cases, we can see that the mean SSI has decreased a bit. The mean SSI outside the cone has not changed much, if anything. The mean SSI inside the cone has changed a lot, and the minimum SSI inside the cone has also decreased a lot. So this confirms the findings that I have just reported. So in terms of conclusions, I think I have shown you evidence that the stress strain index provides an estimate of corneal material stiffness. SSI can be turned into a 2D stiffness map for both healthy and keratoconic eyes. SSI maps can help assess KC progression. So if you compare maps, you can see how much reduction there has been in stiffness, especially in the area within the keratoconic cone. And then the SSI maps have potential for customization of cross-linking treatment. This particular point is really quite important, because if we can tell with some evidence now that the reduction in corneal stiffness is taking place mainly within the cone, then it doesn't make much sense to cross-link a big part of the cornea, but to actually concentrate the cross-linking treatment to the areas that had been affected, which is basically the cone area. And I hope that these findings will persuade some people to move in that direction and to develop this technology. And then finally, I leave you with the list of our collaborators, the people who have taken part and helped this research, including provision of ideas, provision of clinical data, and also drafting of research papers. Thank you.